If you're on a tubular part, like titanium tubing, and this is a real common application for titanium tubing. It can be a structural part of on the rails. The rear wing is held by what's called a tree. That tree is typically titanium tubing, smaller than this, but it's lightweight, it's strong, does a great job, and it's got to be welded, and it's tube to tube. When you weld tube to tube, it's kind of nice to purge because you can you have to not only shield the outside of the part, you have to keep the atmospheric oxygen and nitrogen we're breathing away from the backside. So to do that, we purge it. We put a shielding gas on the backside, and we also have our shielding gas in the front. And once it's shielded on both sides, you can elevate the temperature of the material and melt it. You can add filler metal, and you can have a quality weld. And that weld will be stronger than the base metal. Since it's generally a little thicker in throat than the base metal, it is a little stronger. But it welds nice. Now let me show you this. On the one end, I just took a little piece of tape, taped it off. The other end, you take your gas hose. These might be long pieces, so I'm just using short pieces like we train with. Again, you take a piece of tape, and you build a little atmosphere that eliminates the air. The air we breathe is great for us, just not good for titanium at elevated temperatures. So with our argon, and we have a dual flow meter, has 2 tubes on it. We can set the flow for the purge, we can set the flow for our torch. With that gas coming in there and flowing past the joint, all we do on this end is perforate the material to allow the gas to escape. You really don't need a lot of gas flow. I'd say only 5 cubic feet, 5 CFH, just a positive pressure in there. You can use quite a bit at first to get it to flow, but you don't want a very high pressure inside that part when you're welding. It'll actually push your weld out. So we want to have it able to flow out the end. Now we have our joint. When we tack it up, we'll put it on a fixture. And I'm actually using a fixture that is used for testing for aerospace. It's called a test block. It's nice in this case because it holds our tube. You can lay your tube in here, and you can put it in there and hold it with any device you'd like, any clamps. Get it in a flat position, get it tight together, and you're almost ready to tack it. One additional thing about titanium is titanium's got to be cleaner than other materials when you weld it. And by cleaner, we mean any oils. If I was doing this in an aerospace application, I couldn't use bare hands. You have real light cloth gloves you use, keeps your body oils off it. The materials themselves have to be cleaned. A real common cleaner is acetone. Acetone is a solvent you can buy at a lot of hardware stores, paint supply stores. It's a great degreaser. Some of the degreasers we've used in the past, the trichloroethylenes and stuff, are not what we want to use on titanium, and they're regulated extremely tightly today. So we use acetone to take the hydrocarbon contamination off the material. For actually removing any kind of oxides on it, a stainless brush is fine. Stainless is excellent. Scotch-Brite is excellent. So we need to clean not only the hydrocarbon off the surface, we need to clean the any oxides we have off there. So now we're actually ready to weld. We've got a shielding gas on the back side. Coming through the part, we've set it up, purge it with probably a high flow rate, 20, 30 cubic feet per hour. Turn it back down about 5 for welding, just so we got a positive pressure in there. And our filler metal is from that chart in the GTAW book from Lincoln. It'll recommend a filler metal. Filler metals for titanium are generally flagged. They'll flag them with exactly the alloy, so you know. And in aerospace, this is a serious thing. These flagged alloys are accounted for when you take them out to your welding station, or accounted for when you bring them back. There's a lot of quality assurance in aerospace. In motorsports, we don't have those regulations, but they're not bad to follow. So we make sure we have the right filler metal. The base metal identification can be an issue. I probably should mention that. In the TIG book and in the titanium book, it talks about the alloys of titanium, 6-4 being the most common. We know in the titanium industry that more 6-4 titanium is made than any other type. And that's Al6-4, aluminum 6%, 4% vanadium. Since that's the most common base metal, if we knew that's what it was, we could use 6-4 filler metal. That'd be a proper filler metal. In some cases, you don't know what alloy that is. You can identify it as titanium, but you might not have a real source on it, which is not a good thing. But we know since it's 6.4 the biggest volume out there, chances are it's going to be a 6.4. But just in case it isn't, in case it's another alloy, a lot of times we'll use commercially pure, CP, filler metal. Commercially pure filler metal, it works well on 6.4. It welds great. It doesn't quite have the strength that 6.4 has, but again, our weld with the reinforcement and the penetration we have is generally a greater throat than the base metal, and it works fine. So in many cases we use CP, especially in the trackside welding when we're not sure what, we don't have the ability to track the base metal identification. But if you know it's 6.4 filler metal is the right one to use. So again, our hands would have gloves on them. Our filler metal's identified, the base metal identified. Take our torch. We're not going to weld today, but this is about how we'd set up. We have our cup down close to the work. And you want your tungsten as close to that surface as you can get it. And you push your pedal down, melt the base metal, add your filler metal, and it welds very nice. It welds like stainless. It welds beautiful. Flows nice. It wets nice. It's nice and shiny. And when you finish that weld, you leave your torch. And one thing you have to get used to in TIG welding is not pulling your torch away when you finish a weld. As you finish a weld, you stop. When you let off the pedal, the aft flow timer in the machine will allow the argon gas to flow and protect that heated metal until the timer runs out. And in the case of titanium, you want to set that timer as high as you can set it. I just got to set it a minute on there. So if you allow that temperature of that base metal to get down under 400 to 600 degrees with the argon shielding, you can remove it safely and not expect the titanium to be affected mechanically. In this case, we're just tacking it. We put a little small tack, rotate it, a tack. And titanium, you want quite a few tacks. It's better to have more tacks than less tacks. Small tacks are better than large tacks, and that makes for a quality weld. When you got small tacks and a good number of them, it keeps the part from moving with the expansion of it when you're welding, and it keeps a nice tight joint, high quality weld.